The formation of spiral galaxies is one of the most intriguing mysteries in the field of astronomy, as these galaxies are not only abundant in the universe, but also uniquely structured, making their origins a topic of intense scientific investigation. Spiral galaxies, like our own Milky Way, are characterized by their beautiful, rotating arms that wind outward from a central bulge. Understanding how these complex structures come to be involves exploring the intricate processes of cosmic evolution, the dynamics of stars, gas, and dark matter, and the influence of external forces over cosmic timescales. This description delves into the key mechanisms behind the formation of spiral galaxies, the theories that have emerged to explain them, and the ongoing research that is gradually unveiling this cosmic mystery. Spiral galaxies are some of the most visually striking objects in the universe, with their elegant disc-like structure, spiral arms, and a central bulge. They are typically composed of a central bulge of older stars, a rotating disk filled with gas and dust, and the iconic spiral arms where new stars are born. These galaxies vary greatly in size, with some containing hundreds of billions of stars, while others are much smaller, containing only a fraction of that number. The disk of a spiral galaxy is generally flat and relatively thin, while the bulge tends to be spherical or ellipsoidal in shape, housing some of the oldest stars in the galaxy. The spiral arms of these galaxies are often sites of active star formation, and their distribution follows a logarithmic spiral pattern, which has been a subject of fascination for astronomers since the early 20th century. The spiral structure itself is believed to be the result of density waves propagating through the galactic disk, although the exact process remains a subject of study and debate. Understanding the origin of these arms and their relation to the overall galactic structure is key to unlocking the mystery of how spiral galaxies are formed. Several theories have emerged over the years to explain how spiral galaxies form. These theories primarily focus on two aspects: the formation of the initial galaxy and the development of its spiral structure. These explanations can be broadly divided into the following categories: the hierarchical model of galaxy formation, the density wave theory, and the role of dark matter and galactic interactions. The hierarchical model of galaxy formation, which is a cornerstone of the lambda cold dark matter (LCDM) cosmological model, suggests that galaxies form from the gradual merging of smaller building blocks called proto-galaxies. These proto-galaxies are clumps of gas and dark matter that formed during the early universe. According to this model, larger galaxies, including spiral galaxies, are the result of multiple mergers and accretions over billions of years. In this model, the merging of smaller proto-galaxies leads to the formation of more massive structures. Initially, these mergers may cause galaxies to become irregular in shape, but over time, the disk-like structure of a spiral galaxy can emerge due to the conservation of angular momentum. As gas is funneled into the center during these mergers, it can lead to the formation of a central bulge. At the same time, the angular momentum of the gas causes the galaxy to flatten into a disk, with spiral arms forming as a result of ongoing processes in the galaxy's evolution. One of the key strengths of this model is its ability to explain the diversity of galaxy types observed in the universe. Smaller galaxies, which are often irregular or elliptical, are thought to have formed through different evolutionary paths, while larger spiral galaxies represent a more evolved stage of cosmic development. The density wave theory is one of the most widely accepted explanations for the spiral structure of galaxies. It was first proposed by the astronomers Lin and Xu in the early 1960s. According to this theory, the spiral arms of a galaxy are not permanent structures, but rather are regions of higher density that propagate through the galactic disk. These density waves are created by gravitational interactions between stars, gas, and dust, causing the material to compress in certain regions, which then triggers the formation of new stars. In this theory, stars within the galaxy orbit the center in nearly circular paths, but the material in the spiral arms moves in a more complex fashion. The spiral arms are essentially regions where the density of stars, gas, and dust is higher than in other parts of the disk. These density waves travel through the disk, moving at a speed much slower than the stars themselves. As the wave moves through the disk, it compresses the material in its wake, leading to the formation of new stars in these regions of high density. One of the main pieces of evidence supporting the density wave theory is the observation that the spiral arms are not tightly wound or fixed in place, but instead appear to rotate in a manner consistent with density waves. The theory also accounts for the fact that the spiral arms are often sites of intense star formation, as the compression of gas and dust in these regions triggers the formation of new stars. Another crucial factor in the formation of spiral galaxies is the presence of dark matter. Dark matter, which makes up approximately 27% of the universe's mass-energy content, has a significant influence on the formation and evolution of galaxies. While dark matter cannot be directly observed, its presence is inferred from its gravitational effects on visible matter. In the case of spiral galaxies, dark matter is believed to form a halo around the galaxy, providing the additional gravitational pull needed to maintain the galaxy's structure and prevent it from flying apart. The halo of dark matter plays a vital role in the stability of spiral galaxies. Without this dark matter component, the gravitational forces within the galaxy would not be strong enough to keep the galaxy from disintegrating. The distribution of dark matter in the halo affects the motion of stars and gas in the galactic disk, influencing the shape and dynamics of the galaxy, including the formation of spiral arms. Galactic interactions and mergers also play a key role in the formation of spiral galaxies. While the hierarchical model suggests that galaxies form through the merging of smaller protogalaxies, the process of merging between larger galaxies can also lead to the formation of spiral structures. When galaxies collide, their gas and stars can interact in ways that trigger bursts of star formation and reshape the structure of the galaxy. In some cases, galactic collisions may lead to the creation of new spiral galaxies, or the transformation of elliptical galaxies into spirals. The study of spiral galaxy formation has been greatly aided by advances in observational technology, such as the Hubble Space Telescope, which has provided high-resolution images of spiral galaxies in various stages of their evolution. These observations have allowed astronomers to study the detailed structure of spiral galaxies, including their spiral arms, central bulges, and star formation regions. By comparing galaxies of different ages and sizes, scientists have been able to gather insights into the processes that drive their formation and evolution. In addition to direct observations, computer simulations have become an invaluable tool for studying the formation of spiral galaxies. These simulations model the behavior of gas, stars, and dark matter under the influence of gravity and other forces. By running simulations that incorporate various theories of galaxy formation, scientists can test different scenarios and compare the results with real-world observations. These simulations have provided valuable insights into the role of dark matter, the dynamics of galaxy mergers, and the development of spiral structures. Despite the progress that has been made in understanding the formation of spiral galaxies, many questions remain unanswered. One of the biggest challenges is understanding the precise mechanisms that lead to the formation of spiral arms. While the density wave theory provides a useful framework for explaining the spiral structure, it is still unclear how these waves are generated and sustained over time. Additionally, the role of magnetic fields, supermassive black holes, and other factors in shaping spiral galaxies is not yet fully understood. Another ongoing area of research is the relationship between spiral galaxies and other types of galaxies, such as elliptical galaxies and irregular galaxies. Some scientists believe that spiral galaxies may evolve into elliptical galaxies over time, while others argue that the two types of galaxies have distinct formation pathways. Understanding the connections between different galaxy types is crucial for piecing together the larger picture of galaxy evolution. Recent advancements in observational techniques, such as the study of galaxies at different redshifts, are helping to shed light on these unresolved questions. By studying the formation of galaxies in the distant past, astronomers can gain a better understanding of how spiral galaxies formed and evolved over cosmic time. The formation of spiral galaxies remains one of the most fascinating and complex puzzles in modern astronomy. While much progress has been made in understanding the key mechanisms behind their formation, including the roles of dark matter, gravitational interactions, and star formation, many questions remain unanswered. Through a combination of observational studies, computer simulations, and theoretical models, scientists are gradually unveiling the mystery of how these elegant and dynamic structures came to be. As technology continues to advance and new discoveries are made, we are likely to gain even deeper insights into the processes that govern the formation and evolution of spiral galaxies, further enriching our understanding of the cosmos.